Waves outline notes. So here's the outline that we're having you do on waves. I know you can't really read this from where you're sitting. That's fine. You have a copy of this. Maybe you should take that out while we're going through this. I want you to outline this the way we've done everything. Shouldn't take you very long, really. But there are some definitions, some concepts in here that we didn't have time to cover when we were doing waves a couple weeks ago. So, hey, we're gonna do the best we can today. Now, here's one other thing too. As you're writing these outlines, you have your textbook. You also have this wonderful thing they've just invented called the Google. And if you type in these questions, like transverse wave, if you just type in, draw a transverse wave. If you don't remember it, type it in Google. You're going to get more information on transverse waves than you really need. You just need the basics. So I want to encourage you to use Google to find really good pictures and videos and explanations of this stuff. And it'll work. It'll work just fine. Okay, so let's go through the waves outline. 4, this is outline number 4. Okay. And 4A. It says students know waves carry energy from one place to another. Hey, guess what? Waves carry energy from one place to another. I'm talking to you right now. I'm talking to you through sound waves. My voice is doing work against the air, transferring energy into the air. That energy moves through the sound as a longitudinal wave and does work on your eardrums. And that which transfers energy, and eventually it ends up in your brain. Hopefully. And so it's a transfer of energy. Light is an electromagnetic wave that transfers energy through waving energy packets called photons. We'll talk about that in a few minutes. But all waves is a transfer of energy. If it's a mechanical wave, it's moving through a material medium. If it's an electromagnetic wave, it's moving through empty space all by itself. Okay. B. Students know how to identify transverse and longitudinal waves in mechanical media, such as springs and ropes, and on the earth, seismic waves. Okay, so now that's where we're at right here. Okay, 4B. Now, I'm not going to repeat myself on all of it. I'm not going to do the whole thing. We've already talked about transverse waves, and examples of transverse waves, longitudinals, examples of longitudinal waves. So look through your notes. Make sure you know the difference between a longitudinal wave and a transverse wave. A lot of you didn't on the waves test. So you need to restudy that. Add that. These should be done with pictures. Okay, so draw pictures of that and you'll get it. Okay, C. There is one thing for B that we didn't cover, so let me add something here. We didn't really talk about seismic waves very much. Well, not at all. Seismic waves. What are seismic waves? It's the kind of waves you get when there is an earthquake. Okay, and there are two basic kinds. One of them are called S waves. S waves, what does the S stand for? Nope. Good guess though. Surface. And these are the surface waves. And the surface waves means that on the surface, it's actually a transverse wave along the surface of the ground. So here's the ground. And it actually, these are this is the ground rippling, going up and down and up and down. In 1989, October of 1989, there was an earthquake in the Bay Area called the Loma Prieta earthquake. And my brother lived in Santa Cruz at the time. He lived in the Santa Cruz Mountains. He's probably lived as close to the epicenter as any human being did. Very, very close. Very violent earthquake. He was in he was in his house, and the earthquake was so strong, it was shaking the building so badly that it was throwing things across the room. It wasn't like things were falling off the wall or off of like shelves. They were being thrown across. So at first he got underneath a door frame, and then he said, heck with this. And he just took off, and he ran out the front door, and he dove onto the ground. So my brother, who's 6'8", by the way, and taller and skinnier than me, he was laying on the ground, and said it was like he was a ball being dribbled. He said the ground was just tossing him up in the air, and it was these surface waves. And he said it actually kind of hurt. It was like bam, 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 bam. He's getting bounced up and down on the ground. Then there's another wave. They call it a P wave. And this is and P is for pressure. It's a pressure wave. And this is a longitudinal wave. That is, like this is a transverse wave, right? The amplitude is transverse to the direction of the wave motion. But in a pressure wave, so here's the ground, and the ground actually moves back and forth like this. So if you were sitting there, the ground would go jung, 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 jung. And that's about the frequency, by the way, of an earthquake. It's kind of a jung, 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 jung. Have you ever seen a picture of like a convenience store? They have those video cameras, and they always show the convenience store or an office or something when the earthquake hits, and they're getting shoved back and forth. Well, that's the pressure wave hitting, and it's a longitudinal wave. So you have the S waves and you have the pressure waves, or surface waves and pressure waves. So if you're a seismologist, you study this kind of thing. Some of you might go on and become architectural engineers or architects. Architects have to make sure that their buildings can survive an earthquake, and they need to understand the nature of these waves so that they'll build buildings that won't collapse. So anyway, that's what you need. S waves, surface, transverse. P waves or pressure waves, they're longitudinal waves. Okay, C, 4C. Students know how to solve problems involving wavelength, frequency, and wave speed. Okay. Now this is, velocity equals frequency times wavelength. We did a whole bunch of problems where you did that. I'm going to assume that you know that. Also, I want you to add this. The period of a wave is equal to 1 over the frequency. You need to know that. But there is this one thing that we didn't really cover well enough. Oh, by the way, what is frequency? What are the units for frequency, right? Is hertz or waves per second. But anyway, it's this. What is amplitude? How is it related to energy? Well, we did talk about amplitude, but let's take a look at this wave right here. Here's the amplitude of this earthquake, this seismic wave. Well, what if the amplitude was this? Greater amplitude. Okay? So the amplitude is bigger. Or what if the amplitude was bigger on the pressure wave? That means it would move this way and then it would go this way. Much bigger. How is that related to the energy in the waves? The greater the amplitude, the greater the energy. Believe me. Like the sound that I'm using right now to communicate with you. Loud sound has greater amplitude than quiet sound. Quiet sound has low amplitude. Loud sound has much greater amplitude. All right, so kind of makes sense. All right. For D, sound is a longitudinal wave, and the speed depends on the medium. Now, the denser the material, the faster the speed of sound. And it's because the molecules are closer together. The particles that make the substance, if it's denser, those particles are closer together. And thus it takes less time for them to run into each other, and thus the compressions and refractions in the air travel at a faster speed. So, air, water, rock. Sound can travel through all of these. Which one will it travel through the fastest, though? The air. No, the fastest. I'm sorry. The denser the material, the faster the speed of sound. It will travel through rock much faster than it will through air. And then the higher in altitude you get, the less dense the air gets, the slower the speed of sound. So the speed of sound at very, very high altitudes is slower than the speed of sound at sea level. The speed of sound is much faster in water than it is in air. And it's really fast in rock or steel or any kind of solid material. I mean, you're talking 4 or 5 times faster than in air, because the particles are closer together. So when you have like in air, the air molecules are really far apart. So when it takes some more time to run into each other, and the pressure wave, the compression or the refractions, takes longer to be transmitted. In rock, the particles are very close together, very dense. And so if I smack into this molecule, it doesn't take much time for it to smack into the next one, and the compression just travels through the material very, very fast. E. Here we're going to talk about the electromagnetic spectrum. Okay, now low frequency, high frequency. Now, light, visible light, or radio waves, or X-rays, or ultraviolet light, or infrared, it's all the same stuff. It's all energy contained in the wiggling of electric and magnetic fields. Now, for most of you, this is just words, but you'll take more physics hopefully in the future, many of you, but if I have light as pure energy, if I have actually let me try to do this on the document, because I am trying to videotape these. This is hard to do. Let's zoom all the way out. If I have an electric field and I wave it, that is, I'm changing it with time. I'm waving an electric field. Well, whenever you change an electric field, you create a changing magnetic field, but the magnetic field is perpendicular to the electric field. But if I have a changing magnetic field, that will create a changing electric field. Changing electric fields induce changing magnetic fields. Changing magnetic fields induce changing electric fields. And what they do is they do this. Woof. Isn't that cool? All right. I call this the Photon Dance. And if And what it is, it's pure energy contained in these electric and magnetic fields, and they induce each other. And this is why electromagnetic waves, X-rays, visible light waves, they don't need a medium because they induce each other to travel through space. Now, the only difference is at what frequency. If I have something that's made at a very low energy, like radio waves, they'll go really slow. They'll wave back and forth very slow, not very much energy. But then I increase the frequency. Okay, now I've got microwaves. And then I increase the frequency some more. Okay. Now I've got infrared light. We can't see it. We can't see it, but it's there. You feel it. Then we have visible light. Visible light is fairly fast. Here's red. Increase the speed a little bit, increase the frequency, now you got blue. And then you go beyond visible light and you go to ultraviolet. Okay, you can't, you know, ultraviolet, it gives you a sunburn, right? And then you go beyond ultraviolet and you have X-rays. Okay, now they are within each other. Okay, there's X-rays. And then you get to the highest frequency electromagnetic radiation detectable. It's called gamma rays. These things are bad, okay? Gamma rays will kill you. They kill you, all right? Gamma rays are they're almost like little particles of pure energy. And if they go into your body, they have so much energy they can actually break apart your DNA molecules. And you can get cancer or mutations, or your children will have 4 eyes or something like that. Okay, I mean, or 3 arms. I mean, it's bad stuff. So, here's how I like to do this. Radio. Okay, let me zoom in. Radio waves. Very low frequency. Now, by the way, you know, you have very power waves, they're called, very, very, very low frequency. Then you have like AM radio, which is measured in kilohertz. Then you have FM radio measured in megahertz. And then you get into microwaves, which are still fairly long wavelength compared to other things, but this is the kind of wave-like packets of energy that microwave ovens make. And these interact with the water molecules in food. So you put your food in the microwave, and what it does is that these waves interact with water molecules and make them vibrate and gives them thermal energy and heats up your food. But not all molecules will vibrate at that frequency, so it doesn't heat up some stuff. All right. Then you get to infrared. These have higher frequency, greater energy. Infrared light. Now, we can't see infrared light, but if you hold your hands up to a campfire and you feel the warmth, or you feel the warmth of the sun on your face, okay, that's infrared light. And we do have cameras that can see in the infrared, right? I mean, if you're in the military, you wear night vision goggles. They're seeing the infrared light given off by everything. Anything that has a temperature gives off infrared, you know, and we can, we have cameras that can see it. Then we have visible light. And visible higher frequency, it's a very small range of frequencies. Red is the lower visible frequency, and then blue is on this side. So you get Roy G. Biv, you done Roy G. Biv, red, orange, yellow, blue, red, orange, yellow, green, blue, indigo, violet, or something like that. So the blue is kind of on the higher, indigo and violet. And then we have ultraviolet. Ultraviolet light. Now ultraviolet, it's at a high enough frequency where your eyes can't see it anymore. You don't have, there are creatures whose eyes can see a little bit into the ultraviolet and a little bit into the infrared. Yeah, I mean, yeah, and it's kind of interesting. It depends on the creature. We've got very good vision, by the way, compared to many creatures. We can see color. Many animals really see only in black and white, but we can see in color. So we're very lucky. People are always putting humans down, but we're pretty amazing. All right, then you go past ultraviolet, you get X-rays. And this is what the dentist will shoot into your face. Well, if you get too much of it, it increases your chances of getting cancer. This has so much energy that it can cause genetic damage and therefore can cause cancer. Nowadays, X-ray machines give you such a low, or they're so sensitive and they give off such a low dose that you're pretty safe. Then, gamma rays. They call them rays, but it's really a wave-like packet of energy. Super high frequency. Tons of energy. Well, tons, that's not a very good unit for energy. But lots and lots and lots of energy. What makes these? Exploding stars. Thermonuclear explosions. The most high energy things that happen in our universe create gamma rays, and you want to stay away from them. Happily, our atmosphere and our atmosphere blocks gamma rays from reaching us. There are stars in our universe that explode, and they give off gamma rays. And if we didn't have an atmosphere, we'd have a little bit of, we'd be in danger. Astronauts who go into space have to be, well, you know, if we're going to have a future in space, we're going to need to learn how to protect ourselves. This is the electromagnetic spectrum. And the basic thing to know this, radio, microwave, infrared, we're gradually getting higher and higher and higher and higher in frequency, higher and higher and higher and higher and higher and higher and higher in energy. Okay? But it all travels at the same speed, the speed of light. C is the speed of light. And the speed of light is 3 times 10 to the 8 meters per second, which is pretty close to being 186,000 miles per hour? No, miles per second. Okay, how fast is that? Okay, imagine you go outside right now and you run around the circumference of the Earth 7 times in 1 second. That's the speed of light. Go from here to the moon in a second and a quarter. Okay, that's the speed of light. It's fast. But on the scale of the universe, it's actually pretty slow. If you wanted to send a light signal to the nearest star, to our star, Alpha Centauri, it'd take you over 4 years. You send a little SOS signal with a flashlight, they'll see it 4 years from now. And that's the closest one to us. So, and as far as we know, nothing goes faster than the speed of light. That's the speed limit of the universe. Okay, next, as we cram and cram. Index of refraction. That's right here. Index of refraction. Look, the index of refraction tells you how much the speed of light slows down in a material and how well it bends light. So the higher the index of refraction, the slower light travels through it, and the more it will bend light. Okay, these, my glasses right here, okay, they bend light. Look at them bend the light. The text behind there, see how it gets all bent? I can't see it because I'm blind without my glasses. High index plastic, my glasses are made out of. Okay. Okay, let's do well, we can try to keep it all on the same page here. We've got room. 4F. Now, some of this stuff we've already talked about, and I'm not going to re-lecture on it now because we're running out of time anyway. We've got interference. I want to explain what interference is. That's the way the amplitudes of waves add. If they add together, you have constructive interference. If they cancel each other out, that you have destructive interference. Diffraction, that's the bending of waves around a barrier. Refraction, that's the bending of waves because it's changing mediums and the wave is slowing down or speeding up. But I want to talk about these last two things, the Doppler effect and polarization. Let's talk about the Doppler effect. If you have a car, could be a train, they use trains or cars. Here's my car. Let's say it's a race car. You know what, I'll make this a race car. Here's the other. It's like the Indianapolis 500's coming up. Here's one wheel. Here's our driver sitting in here. There's a little windshield. So there's our race car. Have you ever watched a NASCAR or race car on television? And they have a camera, a TV camera down on the track. So here's the little TV camera on the track. It's gonna drive by it. And they also have a microphone to measure the sound that the car gives off. Now what do you hear as the car goes by? I mean, have you ever listened to a car race on television? Here's what you hear. Right? As the car goes by. Right? Okay, you're laughing or snickering or whatever, but you know it's true, and that's pretty good, isn't it? Now, if you're the driver in the car, this is what the engine sounds like. About like that. But if you're over here, the sound waves are squished in. Why? Because the car is moving really fast. Now these waves are moving really fast, the speed of sound, but the car is moving too. And what it's doing is it's squishing in the waves. So the waves sound closer together. The wavelength is less. Therefore, the frequency is greater and it sounds at a higher pitch. So even though if you're the driver, it sounds like this, but if you're the microphone that the car is approaching, it sounds like this. Higher pitched, higher frequency. But if you're the camera that's over here with the microphone, the sound over here is being stretched out. Why? Because the sound is moving with this speed, but the car is moving with this speed like this, so now the waves have to go farther, so the wavelength is greater, and the frequency is less, and it sounds lower. So as the car drives by, it goes like that. It shifts down in frequency. Have you ever heard this, like somebody's honking their horn as they're driving by you on the highway? And it goes, that's the shift in frequency that you hear. That's called the Doppler shift. Light does the same thing. If something is approaching you at very high speed, the light gets shifted towards the blue, towards a higher frequency. If something is moving away from you very fast, the light gets spread out and it looks redder than it should. That's why they call it the red shift. So the Doppler effect is something you should look up. Yes?
What's the speed of sound?
Depends on where you are, but it's about 340 meters per second where we are. 343 meters per second. About that. Okay, last thing. Polarization. sometimes light can be oriented in all different directions. So here's the waving light, and it can look like this, like this, like this. If you put it through a polarizing filter, it has slits in it. These are like the glasses that you wear at a 3D movie. And it only lets the light through that oscillates up and down like this. And so now your light will look like this. Now this is the light coming at you. I said that light oscillates. You know, like we had the light down here and it's going boom, 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 boom like this. Well, if you're looking right at the light, like somebody shines a flashlight in your face, some of the light oscillates this way, some of it oscillates this way, some of it oscillates, all different directions. Polarized light only oscillates one way. Okay, and in a movie, 3D movie, like here you're wearing here are your sunglasses, right? Or the glasses, the 3D glasses that you wear in a movie. This eye will only let light in that's oriented this way. This eye will only let light that's oriented that way. And then they actually show two different pictures on the screen. But your left eye only sees one image, your right eye only sees the other image, and then your brain puts them together to make a 3D image. Fascinating stuff. Anyway, you can look that up, by the way, polarized light. That's something you can do the Google thing with. Hey, the Waves outline is due on Monday.